let's continue with the part 4 of a series of lectures about graph connection Laplacian and the vector diffusion map. And the focus on this lecture will be how to analyze a set of point clouds that is sampled from a manifold when we cannot access the geometry of a manifold. So let's recall the manifold model and what we can do so far. So assume the data, the point cloud is located on a manifold, and the manifold is smooth, compact, everything is good, and we assume there is no boundary. When there is a boundary, then we can do something similar, but it's just more complicated. You can find literature, you can find the results in the paper. And we denote Tm to be the tangent bundle associated with the frame bundle Om. Okay, and we denote Pyx to be the parallel transport of the tangent bundle. And that is the overall global picture. Omega is the event space, this is manifold, embedding random vector, and so on. The data is embedded in our p-dimensional Euclidean space. Okay, so recall what we discussed last time. What we discussed last time was, hey, look, we first sample n point, IID, okay, from a manifold. And we will assume the sampling is uniform. Okay, to simplify the discussion, if the sampling is non-uniform, then all the algorithms can be modified using alpha normalization, just like what we did in diffusion maps and so on. But we focus on uniform sampling to simplify the discussion. And we also assume there is a vector field, smooth, then we can sample it. But the question is, vector field is an abstract subject, so how to save it in the computer so that you can do the computation. In a previous lecture, we assumed that we can access the frame bundle. That is, for every point on the frame, we can determine a point on the frame bundle so that it plays as a row of the basis of the abstract vector space of the tangent space. And you can represent the vector field sampled at xi using the basis gj, so that you can save it as a coordinate in the computer so that you can do a computation. So that is what you can do. Okay? Assume, this is the assumption, we can access the frame bundle. Second assumption we had was, hey, look, after you have the sample point, after you can determine, discretize a random vector field, a vector field, then what can you do? What can you do to kind of find the relationship? You determine the edges just like before, and then you build up connection by parallel transport. That is, you assumed that you can access the parallel transport, so that you can determine Gij to be Gi inverse Pxij Gj. That is, you convert a coordinate back to the tangent vector field, and do parallel transport, and convert it back into coordinates. So, as we discussed last time, sometimes it is given, but if not, we have to estimate it. Now this is the mission. In general, we do not have an access to the frame bundle. We do not have an access to the parallel transport. Then what can we do? So this will be the practical implementation from a point cloud, so that we can get more geometric information than just using diffusion maps. Okay, so how to implement graph connection of Laplacian vector diffusion map given a point cloud located on a manifold? That is equivalent to how to construct the practical quantities like tangent space, the frame bundle, and the parallel transport. We don't know them. Then what can we do? And this is the data I give you. So there will be two steps. Step 1, we have to estimate tangent bundle or frame bundle. Second step, we have to estimate the connection. Okay, good. How to estimate the tangent space and the bundle in the frame bundle? What we do is first you fix epsilon PCA to be a bandwidth for the local as a positive value, and you denote n xi epsilon PCA to be all the neighboring points of point xi that is within the epsilon PCA distance. And then remember here, because we do not have access to the geometry, so we don't know geometric distance, geodesic distance. We only know the Euclidean distance. So we use Euclidean distance to approximate geodesic distance, so that this neighbor is very close, it's very close to a geodesic goal, but it is not really. And we denote ni to be the number of points inside the neighbor. Then we form an np by ni matrix called local data matrix in this way. xi1 minus xi, xi2 minus xi, etc. That is, for all the points, neighboring points is centered with xi. This is xi called local data matrix. P is the dimension of the data, which is the ambient space dimension where of the Euclidean space that the manifold is embedded. Okay? So once you get the local data matrix, you can run SVD to get singular value decomposition, where UI is an orthogonal matrix of size P, VI is an orthogonal matrix of size capital Ni, and the sigma I is a matrix of size P by Ni that includes the singular values. Finally, the final step is you can estimate the tangent plane Txim by the first D columns of left singular vectors Ui. Okay? Then you set Bi to be the first D eigenvector, singular vectors. SBI. Here I put D hat, but this is actually just D, because in general we also don't know the dimension, so we may need to estimate D, and so sometimes we have to estimate the D, but we don't discuss the estimation of dimension here, but I assume this is a good estimation, so I put D hat here. So what do we have? We set Bi here, and I say, oh, this we can estimate tangent space Txi by the first D columns. What do we do? So locally, let me use the blackboard. You have a manifold. Locally, it is actually, because it's a manifold, it can be well approximated by a tangent space. Or it can be well approximated by an affine, D-dimensional affine subspace. Okay. Usually we also denote this embedding one as a T star, and this is embedded in RP. So what it tells you is locally near xi, all the points in the neighbor can be well approximated by a D-dimensional subspace. So if you apply SVD singular value decomposition, all the singular vectors will expand this D eigenvectors. The top D singular vectors will approximate this tangent space. And so what you have is actually you get a basis of the tangent space by Bi. And this Bi plays a role as an estimate of a point on the frame bundle, which is a basis of the estimated tangent space. The span of Bi will be the embedded tangent space, or an affine subspace that will approximate the manifold local. Okay, so Q hat is a collection of Bi from all the sampling points. Q hat. This is actually an estimation of the frame bundle discretization. Okay, and if you do all possible rotations of this D eigenvector, you can actually recover the frame bundle, and you can estimate the frame bundle. Okay, and the span of the span of the basis Bi will be an approximation of embedded tangent space. And there is a very simple relationship with local PCA. So for example, if you consider 1 over n, xi transpose, this guy is actually the local covariance matrix. And this local covariance matrix is what we use in the principal component analysis, or we call local PCA because everything is local. And you have singular value, you have eigenvalues, and eigenvalues are square of the singular values. So they are related in this way. And this UI is the left singular vector, singular vectors, and in the local covariance matrix eigen decomposition, this is the left. And they are kind of equivalent, but in some cases, SVD may be better. In particular, when P is very large. That is when the ambient space dimension is very, very large, then maybe SVD is faster. But when you have many points, but the ambient space dimension is very small, maybe local PCA, this eigenvalue decomposition is faster. Whatever, they are equivalent. Then the final step is estimating the parallel transport or connection. And the algorithm is actually very simple. To estimate to estimate the connection in between I and J, what you do is you calculate OIJ, which is the arcmean of O minus BI transpose BJ. Remember what is BI? BI is a basis, a basis that estimates the tangent, the embedded tangent space of Xi. So this is the picture. TXIM, and this is TXJM. And you have basis XBI here, and the BJ there. And clearly, BI and the BJ, they do not span the same spaces. So if you have BI transpose BJ, obviously this guy cannot be an orthogonal matrix. If it is not orthogonal, what we do is we fit an orthogonal matrix to it by minimizing the Hilbert-Schmidt norm of O minus BI transpose OJ. And what you see is, hey, BI transpose BJ is not orthogonal due to the curvature, because of curvature. And then you run singular value decomposition of BI transpose BJ, and then you can calculate OIJ to be UV transpose. So this minimization can be quickly evaluated by SVD. And turns out this OIJ is an estimator of the parallel transport from XJ. This is from XJ to XI. And theoretically, that is what you can say. Suppose I and the J have geodesic distance smaller than square root of epsilon, and suppose X is C3, then with high probability, like 1 minus n raised to power minus 2, OIJ is related to the true parallel transport in the following way. First, remember parallel transport is functioning on the vector field. OIJ is functioning on the Euclidean space RD. So they are related via the basis. First, you have X, you do parallel transport, right? Then you get a vector field, then you embed it into the ambient space, then you evaluate its coordinate by BI transpose. Then this guy, parallel transport, is related to, if you evaluate the parallel transport, the embedding, and you evaluate its basis, then you apply OIJ. Then they are equivalent up to order epsilon 3 helps. So it tells you that OIJ, in this sense, approximates PXIXJ up to order epsilon 3 helps. So it says that at least we know how to estimate parallel transport locally. So you can extract more geometric and topological information directly by structuring the sampling points via connection. And you can still get point-wise and spectral convergence, and obtain connection Laplacian. And once you get connection Laplacian, you can get several useful information. For example, you can get the most parallel vector fields, you can use Bochner formula to get Hodge Laplacian if you can estimate the region curvature, and so on. And you can generalize the whole idea to general principal bundle vector fields forms to help you to access some topological information. And we will see more information later. And this is the, oops. And you can see the theoretical results in these papers, as I mentioned. Okay, and this is kind of the simulation. You can get, for example, in S2, you get 6, 10, 14. This is the multiples of different eigenvalues, which is very beautiful. In S3, S4, S5, and what you can say is, why do you get 6, 10, 14, which sounds a bit weird? That is because of the complex structure. And you get some kind of, you access S2 is a Riemann surface, so you can get some extra things, which is quite nice, isn't it? This is directly from UC point clouds. We do not assume we can access the geometry, okay? And you can get everything almost recovered. And this is an example of vector diffusion distance, which just shows you that vector diffusion distance can help you to recover local geodesic distance, where the x-axis is the true geodesic distance, the y-axis is the vector diffusion distance. And you can see that locally it's like linear. But when you go away, then it starts to become weird. And this one is kind of, it's hard to interpret, because we only have theoretical interpretation when time is small. And this is the picture, how the geodesic distance are related. This is a distance, this is distance.